Good morning, everyone. I am delighted to welcome you all today. Today, we will be exploring the important topic of photostability testing of new drug substances and new drug products. My name is Dr. S.K. Singh, and I hold a PhD in this field. Over the course of this presentation, we'll cover the key principles, methodologies, and significance of testing how drugs withstand exposure to light. I hope you find this session informative and engaging. Let's get started. Let's talk about the intrinsic photostability characteristics of a drug substance and product. It's important to evaluate these to ensure that light exposure doesn't cause unacceptable changes. Essentially, we want to make sure that the drug remains stable under typical lighting conditions. Photostability testing is performed on a single registration batch of both the drug substance and the drug product. This helps confirm their robustness against light exposure. Now, a systematic approach is recommended for this testing process. First, we conduct tests directly on the drug substance itself. Next, we test the drug product outside its immediate packaging to see if light causes any changes. If we observe unacceptable changes outside the immediate pack, then the next step is to test the drug product within the immediate packaging. This is crucial because the packaging can offer some protection, but we need to verify its effectiveness. And finally, if the change remains unacceptable even within the immediate packaging, testing should be conducted on the drug product in the marketing pack, the packaging as it will be sold to consumers. It's important to note that acceptable change means any change that stays within limits justified by the applicant, meaning the manufacturer has provided a valid rationale. We also need to distinguish between different types of changes. For instance, a change in appearance, like color or clarity, can be justified by the applicant if it doesn't affect the drug's safety or efficacy. On the other hand, decomposition, which involves breakdown of the drug, has specific limits outlined in the ICH guidelines on impurities in new drug substances and products. These guidelines help us determine what level of decomposition is acceptable. Overall, this systematic and thorough approach helps us ensure that the drug remains safe, effective, and stable throughout its shelf life under various light exposure conditions. When we're looking to distinguish between the effects of light and temperature on our samples, it's important to control these variables carefully. The temperature should be appropriately controlled, or alternatively, we can use a dark sample as a reference point. This helps us isolate the specific influence of light without temperature interference. Now, when we talk about light sources for testing, the goal is to mimic natural daylight as closely as possible. For this, we often use sources designed to produce an output similar to the D65 or ID65 emission standards. These standards are internationally recognized. For example, artificial daylight fluorescent lamps, lamps that combine visible and ultraviolet outputs, or even xenon or metal halide lamps can be used. D65, in particular, is the standard for outdoor daylight, as specified in ISO 10977 from 1993. It's mainly applied for photographic materials, ensuring consistent and reliable light conditions. ID65, on the other hand, is the indoor equivalent of this standard, providing a comparable light environment for controlled indoor testing. Understanding and using these standardized light sources helps us ensure our results are accurate and reproducible across different settings. For option 2, the same sample should be exposed to both types of lighting. First, the cool white fluorescent lamp, which is specified in ISO 10977 from 1993. And second, a near-UV fluorescent lamp with a spectral distribution ranging from 320 to 400 nanometers. Now, even with these options, the xenon light source remains the best choice overall because of its spectral qualities. But it's important to understand that we need to differentiate between two key concepts, illuminance and irradiance. Illuminance, which describes how bright a light source appears to us, is measured in lux. Think of it as how much light is falling on a surface. 1 lux equals 1 lumen per square meter. On the other hand, irradiance measures how much energy a light source delivers, and it's expressed in watts per square meter. To put it simply, 1 watt equals 1 joule per second. In German, we often refer to illuminance as Beleuchtungstärke and irradiance as Bestrahlung. So, understanding this distinction helps us evaluate light sources more accurately, whether we're interested in their visual brightness or their energy impact. By carefully selecting and comparing these sources, we can better simulate real-world conditions and ensure our testing is as representative as possible of actual use cases. When we're conducting confirmatory studies, it's essential that our samples are exposed to a specific type of light to ensure consistency and reliability. The exposure must provide an overall illumination of at least 1.2 million lux hours. This means that the total amount of light intensity over the exposure period needs to reach that threshold to simulate real-world conditions accurately. In addition, the samples should receive an integrated near-ultraviolet energy of no less than 200 watt-hours per square meter. This UV component is crucial because UV radiation can significantly affect the material's stability and performance. To achieve these conditions, samples can be exposed side by side with a validated chemical actinometric system, or using calibrated radiometers or lux meters. This ensures precise measurement and control of the light exposure. A common tool used for this purpose is the Suntist CPS from Atlas Corp, which is equipped with a xenon lamp. The xenon lamp provides a broad spectrum of light that closely mimics natural sunlight, making it ideal for these tests. Now, regarding the specific radiant exposures, the 200 WH/M2 is targeted within the wavelength range of 320 to 400 nanometers, which falls within the UV spectrum. To achieve this cutoff at around 320 nanometers, a filter system is used, consisting of coated quartz glass and a window glass filter. This setup filters out wavelengths below 320 nm, ensuring that only the desired UV range reaches the samples. The second key exposure, the 1.2 million lux hours, applies to the visible light range, approximately from 400 to 800 nanometers. This range covers most of the visible spectrum, which is important because visible light can also influence material properties over time. In summary, these exposure conditions, both in UV and visible ranges, are carefully designed to simulate real-world lighting conditions, providing a standardized way to evaluate material stability and performance under controlled, repeatable conditions. On this slide, I want to highlight how the irradiance level in the Suntist can be adjusted, ranging from a minimum of 250 W per square meter up to a maximum of 765 W per square meter within the wavelength range of 320 to 800 nanometers. When we install the AM filter systems, these limits translate to specific values in the UV and visible ranges. In the UV range, that's approximately 22.5 WM2 at the low end and about 68.9 WM2 at the high end. For the visible range, we're looking at roughly 55,000 lux to 170,000 lux. Now, let's consider what this means for our test durations, especially in terms of confirmatory studies. For example, in the 320 to 400 nanometer range, if we want to deliver 200 watt-hours per square meter, at the minimum irradiance level of 22.5 WM2, it will take about 8.9 hours. Conversely, at the maximum level of 68.9 WM2, the same energy dose can be achieved in just about 2.9 hours. Similarly, for lux hours, if we're aiming for 1.2 million lux hours, at the minimum irradiance level of 55 kilolux, it takes roughly 21.8 hours. At the higher level of 170 kilolux, it drops to around 7.1 hours. It's important to note that increasing the irradiance levels speeds up the testing process by roughly a factor of 3. However, higher irradiance also causes an increase in temperature, which can influence the test results. That's why we generally recommend sticking to the minimum irradiance level of 22.5 WM2 to keep conditions stable and consistent. In summary, Adjusting the irradiance levels allows us flexibility in managing test durations, but we need to balance speed with temperature control to ensure reliable results. Let's talk about confirmatory testing on a single registration batch. This step is crucial because it provides the necessary information for handling, packaging, and labeling of the drug substance. Specifically, for drug substance I and drug substance II, we need to ensure that all aspects are clearly understood before moving forward. Now, when it comes to photostability testing, it should be divided into two main parts. First, we conduct forced degradation testing early in development using one batch. This helps us evaluate the overall photosensitivity of the material, which is important for method development and elucidating degradation pathways. During these tests, we typically examine the drug substance itself, or its solutions or suspensions. It's important to note that if extensive decomposition occurs during exposure, we should limit the exposure to prevent unnecessary degradation. For materials that are photostable, studies can usually be terminated after an appropriate exposure level has been applied, saving time and resources. Finally, if decomposition products are observed under forced conditions, but are not formed during confirmatory studies, they don't need further examination. This helps us focus on relevant degradation pathways that could impact the drug's safety and efficacy. When examining samples, we look for any changes in appearance, clarity, color of the solution, assay, or decomposition. It's important to check these aspects carefully, as they can indicate stability or potential issues with the sample. If necessary, we take a representative portion of the sample, or sometimes we homogenize the entire sample to ensure consistency. And remember, always compare your results with a protected dark control sample to have a reliable point of reference. When analyzing samples, we want to minimize any changes in their physical state, like sublimation, evaporation, or melting, as these can affect the accuracy of our results. To do this properly, we place an appropriate amount of the sample in a suitable glass or plastic dish. We spread it evenly across the container to achieve a thickness of no more than 3 millimeters. The goal here is to present the samples in a way that allows for uniform analysis. Spreading the sample in a thin, even layer helps ensure consistent exposure and measurement. Overall, the key is to handle the samples carefully to preserve their integrity and obtain reliable, precise results. Now, let's talk about the importance of forced degradation studies. These studies should provide us with reliable analytical procedures that can be used in confirmatory studies. Specifically, they help us in resolving and detecting photolytic degradants that might appear during those confirmatory tests. It's important to remember that these forced degradation tests are part of stress testing. They are not meant to set strict limits for how much change is acceptable, but rather to give us a better understanding of how the drug degrades under stress conditions. Moving on to the confirmatory studies, their goal is to identify key factors that influence the stability of the drug. This includes determining what precautionary measures need to be taken during manufacturing or formulation to ensure stability. Additionally, we need to assess whether light-resistant packaging is necessary to protect the product from light-induced degradation. When it comes to judging the results, the critical point is that these studies help us make informed decisions about how to handle the drug product. They guide us on necessary precautions and packaging requirements, ultimately supporting the overall quality and safety of the product. So, in essence, forced degradation and confirmatory studies are essential tools in ensuring that our drug remains effective and safe throughout its shelf life. In this slide, we're looking at an example of forced degradation studies, which are essential for understanding how our drug substance behaves under stress conditions. First, let's talk about the test samples. We use the drug substance spread in both colorless and brown glass containers, ensuring the thickness does not exceed 3 millimeters. This setup helps simulate different storage conditions. We also prepare 1% aqueous solutions, or inert organic solvents, both with and without nitrogen gassing, all in colorless glass. Additionally, we test the solutions in brown glass. Moving on to the test attributes, we focus on several key factors. the appearance of the samples, clarity of the solution, the color of the solution, as well as assay and decomposition. These parameters help us monitor any changes or degradation over time. Regarding the storage period, the samples are kept for 48 hours under specific light exposure conditions. 5 watts per square meter, which translates to about 1080 watt-hours per square meter, or roughly 2.6 million lux-hours. This intense exposure simulates light stress to evaluate stability. For evaluation, we look at the extent of decomposition. If it's less than 0.1%, the sample is considered not photosensitive. However, if decomposition exceeds 0.1%, we repeat the test after 24 hours to confirm the results. The judgment of results hinges on these findings. Essentially, if the decomposition remains below 0.1%, the substance is deemed stable under light exposure. If it's higher, further testing is necessary to understand the degradation behavior. Overall, these studies are crucial because they help us predict how the drug might degrade in real-world conditions, ensuring safety and efficacy. Let's take a closer look at the test samples we use in this process. First, we have the drug substance spread in both colorless and brown glass containers, ensuring the thickness does not exceed 3 millimeters. This setup helps us simulate different storage conditions and assess stability effectively. Next, we have the 1% aqueous solution, or alternatively an inert organic solvent, tested both with and without nitrogen gassing in colorless glass. This variation allows us to evaluate how oxygen presence or absence influences the sample's stability. We also include a 1% aqueous solution, or organic inert solvent, in brown glass to see how different container types impact the results. Moving on to the test attributes, we examine several key factors. Appearance is important. Does the sample look the same over time? Clarity of the solution helps us check for any precipitates or cloudiness. The color of the solution is also monitored closely, as any change can indicate degradation. Finally, we look at assay decomposition to see how much of the active substance remains after storage. Regarding the storage period, we typically evaluate the samples over 23 hours under a light intensity of 22.5 watts per square meter. This corresponds to roughly 495 watt-hours per square meter, or about 1.2 million lux-hours, conditions that simulate real-world exposure to light and help us gauge stability under typical storage environments. Finally, when we evaluate decomposition, we're looking for a threshold of less than 0.1% degradation at the end of the test. If decomposition exceeds this, specifically over 0.1%, we need to perform structure elucidation to understand what changes have occurred. This step is crucial for confirming the stability and integrity of the drug substance under the tested conditions. When handling samples for light exposure testing, it's important to take care to prevent or minimize any physical characteristics that might affect the results. For example, the sample should be positioned in a way that maximizes its surface area exposed to the light source, ensuring consistent and reliable data. When presenting the samples, the studies should be carried out in a logical, sequential manner. First, we expose the drug product fully, and if we observe any unacceptable changes, we then test the product in its immediate packaging. If the results still show unacceptable effects, we proceed to test the product within the actual marketing pack. The primary goal of these results is to demonstrate that the drug product is protected from exposure to light under normal conditions. This helps us confirm the stability and integrity of the product throughout its shelf life. Typically, we perform these tests on one batch during the development phase and another on a registration batch. This ensures consistency and reliability across different stages of product approval. For the testing conditions, the drug product should be exposed to standard lighting conditions, with the packaging being an aluminum tube, only the exposed drug inside. This setup simulates real-world scenarios, providing meaningful data on how the product withstands light exposure. When working with special labeling, it's important to consider whether additional measures are needed to protect the product from light exposure, which can affect stability. Sometimes, you might need to add specific labels or instructions to ensure proper handling. Additionally, conducting formal stability studies is crucial to confirm that the product remains within its specified quality parameters throughout its shelf life. These studies help us understand how the product behaves over time and under different conditions. When testing the product, we look at key attributes such as physical properties, including appearance, clarity, and the color of the solution. These are basic indicators of quality. We also perform assays to measure the active ingredient content and check for any decomposition products to assess stability and safety. Sampling considerations are vital too. Testing should be done on an appropriately selected composite of samples, meaning we need representative samples that accurately reflect the entire batch. This ensures our results are reliable and meaningful. Finally, the judgment of results involves analyzing the samples carefully. We compare the data against specifications to decide whether the product meets quality standards. All these steps, proper sampling, thorough testing, and careful analysis, are essential parts of ensuring the drug product remains safe, effective, and stable throughout its shelf life. For further support, please contact us. If you have any questions or need additional assistance, don't hesitate to reach out. We're here to help ensure you have all the resources you need. Thank you so much for your attention and engagement throughout this presentation. We truly appreciate your time and interest.